Please come in. We have to start. You're right. Non mi dovete cadere in un sonno dopo questo bellissimo pranzo, mi raccomando.
So please don't fall asleep after this wonderful lunch break. Otherwise, I'll be asking questions about this morning's program. So please, let's focus.
Are you ready, Stefan? Okay. Then we can start with 2 minutes delay, so we are on time. If we consider what our rules by the Swiss Federal Railways. Hi everyone, my name is Marco Corradini. I am from yesterday the new secretary of the UEEIV. And I am a railway engineer. I work for the Swiss Federal Railways in Switzerland in the infrastructure, and I am asset manager infrastructure. Now I will say something in Italian, because we are in Naples. Ieri c'è stata anche una cosa molto importante.
So yesterday something very important took place. I don't know if you're familiar with that. It's very important. I think you have read about it. We have to bring energy into the system. We have to actually not to rest on our laurels because competition is very high. We are here in Naples to represent a part of, a small part, but an important one of the world of transport world. What I read tonight is that the EU Commission on the Committee on Transport actually issued a communication according to which it seems that apparently that there will be a new start. The 10 TNT will be revived with a set of high-speed lines that will have to be implemented in over the next decade, and the member states are invited to actually streamline ticketing all over Europe and simplify rules with an increasingly central role within the European railway landscape. And I do believe in the importance of words, and I do hope this will turn into something real. But in any case, we are part of the system and we have to share energy.
Information. This is a forum. This is the UEEIV forum. There's one in here, every year. But we have also railway talks. Railway talks are about each 2 months. We would like to do more. So if you have interest, please send your application form. We have done a lot of advertising in LinkedIn and in other platforms. Please sustain our system. And we will be happy to have you as participants, as a speaker in our talks. Thank you. And then I will moderate this third session. We have 3 speakers. The first one is from the company Rhomberg, Sersa, is Stefan Vonbun. Come on the floor. Hi, Stefan. Ciao. So, Stefan will give us his presentation on these topics, innovation and international experiences with construction and renewal of Slab Track. Thank you, Stefan. The floor is yours. Thank you. And you have 20 minutes.
Thank you. Does this work? Yeah, all right. The clicker thingy is here. All right, let's go. What does track construction have in common with operating? Operating in a sense of opening someone's body, looking in there, fixing some issues. Maybe you have an idea. Generally, you will rely on what the person is doing and that they are doing a good job, that they know what they're actually doing, and you will completely trust them. Also, the railways are a really trusted way of transport. When you're sitting on a train, working, sleeping, whatever you're doing, you trust that someone took good care of the rolling stock, that someone constructed the tracks that you are running on in a good way, that there won't be an issue, yeah? And you will not think about any dangers, yeah? We feel relaxed, we feel easygoing on trains, and this is because of railway engineers, such as the people we have in here. And yeah, so what railway companies, infrastructure owners are looking for are, of course, proven and reliable solutions, but also people who can actually execute properly, yeah? Because being a surgeon operating, it's not only enough to have the best equipment, a sharp scalpel, or a good light to see what's there, but you also need to know how to actually use those tools. Rhomberg Sersa is such a company that knows how to do these things. We have been constructing slab tracks for 25 years without break, and we are active on 3 continents. And slab track is one of our main knowledge areas and one of our main competences. My name is Stefan Vonbun. I work at Rhomberg Sersa in the headquarters in Austria, next to the beautiful Lake Constance, Lago di Costanza, for the Italian-speaking crowd. And I'm happy to be here today to introduce you to some of our projects that we executed and to talk also about some of the innovations that we actually bring to the market. So, slab track, I mean, there's different definitions of when it was actually established, but let's say around the 1960s, yeah? If you go to Pompeii, not far from here, there is also some kind of slab track I found. Yeah, these are like the little indents they had in the stones, because there were so many wagons passing over it that you could actually consider this kind of a slab track. It's very maintenance-free, yeah, since 79 AD, yeah, and this is actually not my first time in Naples. The first time in Naples was in 1996. This is me at the Vesuvio, yeah. So I already back then was apparently inspecting the slab tracks in Pompeii without even realizing. It's good to be back here and to be talking about slab track. So back to the operation slab track. I see slab track as a system that should be used wherever necessary and possible, yeah. And everywhere else we will have ballasted track. So it's not an either or, it's, for me it's both, yeah. We need the proper systems for the right application. And this is also true for the different kinds of slab track systems. All of them have advantages, disadvantages, and so we really have to think about what is this track going to be used for, what are the main design parameters in that project, and that's how you find a best for project solution. Other things that are necessary for building slab tracks, this is actually also true for what the colleagues from POR and VCE said. They said precision is necessary. Yes, I agree. Precision is super fucking necessary because once it's cast in, you can't move it anymore. Yeah, so you have to be sure that this thing is actually in the right place. Another thing is safety, for sure. Safety is one of the most important topics in the railways, because if we make mistakes, it could lead to potentially to humans being harmed. Yeah. And last but not least, we need brains to do all that, and not just a little bit. I think we need many brains. Yeah, it's a team sport. Building track, and especially slab track, is a team sport where a lot of different people have to interact and have to work together to actually make this a success. I now want to go into a few highlights of projects that were executed by Rhomberg Sersa. The first of which was in Germany. The whole project, let's say, conglomerate of Wendlingen-Ulm and also Stuttgart 21. There we had, for the first time ever, a system in operation that we call ROMAT, which is kind of a track adjustment robot. Yeah? We saw in previous presentations that every top-down system needs to be spindled up and somehow put into place, so the top of rail is actually where it should be. Yeah? Rhomberg Sersa developed this so-called ROMAT, especially for top-down construction, to get into a more automized way of constructing, in this case, Radar 2000 system. Next example, we already heard a little bit about it from the view of POR and VCE. The Corradini tunnel, also a really important project, like a century project essentially in Austria, that is connecting now cities and regions of Austria that were before very far away, so to say. And this tunnel really reduces the traveling time and thus enables people to meet quicker, and it brings economical opportunities to regions that were before kind of cut off inside of Austria. An innovation that we used there was a gantry crane, as you can see on this little video. And the gantry crane was used to place the POR slabs. Yeah? And it can lift 3 slabs at a time. And it was a really efficient way of bringing the slabs into the tunnel and accurately placing them. Build and forget is what I put on this slide, and the sign of a one-way street. Because I mean, we know that slab track has a design life of 60 years or maybe 90 years, yeah? But not everything always goes according to plan. So either you might have an accident happening, or there's other things that actually make it necessary to deconstruct, to disassemble a slab track and rebuild it, yeah? So the build and forget is not really a philosophy that we're aboard with. I think you have to think to the end of the life cycle as well. The planned life cycle, but maybe also the life cycle when it ends earlier than expected. Here you can see a picture from currently taking place refurbishment in Germany, Hamburg, Berlin, where they are actually cutting out track slabs. Yeah, this is a quite tedious work. Because I not only want to talk about newly built track, but also refurbishments. Some pictures from Gotthard Tunnel. We saw in the previous presentation of Thomas Dorfner mentioning of LVT system in Gotthard Tunnel. Unfortunately, there was an accident there with a derailment, and in the end, this had to be refurbished. And for the sake of speed, high accuracy of the final product, and probably also because the insurance was paying for it, the way of completely deconstructing and building it up newly was the chosen path. Yeah? So they didn't go for what is potentially possible, replacing the blocks. In the end, we milled out all the concrete and reconstructed the whole slab again with LVT. And also here, the accuracy is of course very important. Otherwise, you end up with a system that you have to ride on for 60 years, and if that's not accurate, then you have a problem. So, Rhomberg Sersa, as a company, has built more than 800 kilometers of slab track in the past 25 years. So we have a really proven track record of building slab track. And like every inventor, we thought, okay, some things can still be improved about the systems that are out there. So we have heard today a lot about top-down systems, yeah, where we actually have to put the top of rail in the correct position, and then we cast the whole system into place. There's also bottom-up construction, where you have higher levels of prefabrication, and you use less on-site grout or concrete. And so Rhomberg Sersa developed a system that combines these two worlds, yeah, and takes advantage of the good things of each type of construction. When I last year interviewed a lot of our guys who actually built these systems, this is what actually stuck out to me. The guy said, Stefan, is as easy as constructing with Lego. Yeah? And me being a long-term Lego fan, I was happy about this analogy because I think it works really well in describing how our system works. And so, of course, I had to make a Lego out of a Lego version of our system. And if we talk about the construction of IVEs, that's the name of our slab track system, it goes really easily. You have an asphalt base, similar to what the colleagues from POR were describing earlier. We add prefabricated blocks, and the very, let's say, different part is we use a direct fastener, yeah, which is cast in place on site. And you end up with a really fast to build and reliably stable slab track. Also noteworthy is the fact that it doesn't matter whether you are on a straight track or you go into a curve. You don't need a special type of block or slab. So adhering to the example of the world of toys, you all know these wooden railway tracks, yeah, that children use. They're very easy to build. It's quite hard to make this into a curve. So either you end up with a polygon or you have a different piece of track, you need a curved piece, yeah? And in the room of your children, it might be easy to manage the logistics of these two. But imagine a 33-kilometer long tunnel somewhere out in the outback of Austria, and then you end up with a huge logistical question mark. How to bring the things there. You have to be just in time, just in sequence, and with the ice block, you don't have this topic, and down to radii of 40 meters, you can use the exact same block no matter where you go. You can even stock them. You can stockpile them and have them on in a warehouse. If there's an accident, you just take the blocks from the stockpile and replace the ones that are there. Talking about replacement, because this system still adhering to the Lego philosophy, yeah, is just a positive interlock between the block and the bottom surface. So we are using a type of shear dowel. You can see it a little bit here on the left-hand side. You can see it better on the Lego version. It's essentially a stainless steel tube, yeah, that helps to transmit longitudinal and transversal forces. And by means of this dowel, it's fixed in place, but you can still, if you lift it up, you can remove the blocks easily and exchange them in a case of emergency. A lot of people would say, okay, that's all nice and good, but does it actually work, and how does it behave in track? Yeah, this is a very good question, because laboratory tests, etc., are fine, but it's better to actually test the things out in the track. This special piece of track is actually a weighbridge. So trains that run over it are being weighed when they run. It's located in eastern Australia, and the trains that travel over it are coal trains, and they transport a lot of coal there, 30 tons axle load, and very long trains all year long. And our system has been in place there since 2017. And we have accumulated 1,230 million tons, or 1.2 billion tons, in just shy of 8 years. And if you compare that to, let's say, regular mainline loads in Central Europe, you would end up with an equivalent operating time of about 62 years. If we would take the Langenleban example, where POR had installed their slab for the first time, where they have 40 MGT, okay, then we would end up with 31 years of, so to say, real-life simulation of the lifetime. And because this works there so well, we got together with the client, with ARTC, and wrote an article about it that was published in October, so just recently, in the magazine ZEV Rail, which is a German-speaking magazine, but we are also working on an English translation of this article. Also worth to mention, the blocks that we used in Branxton in Australia are not pre-stressed. There's only slack reinforcement in there. In other places we have also used the pre-stressed versions, but I think it goes to show that if these blocks can withstand 30 tons axle loads for a long time, they would also be suitable for other applications without having the need for pre-stressing. And we actually had that in mind when we designed it, but in some countries the regulations kind of forced us to use pre-stressed reinforcement. And talking about different countries, we are very happy that recently we received the EBA approval, the approval of the German Federal Railway Federation, which is a kind of Leitmark and or a lighthouse approval and a really good cross-reference opportunity, because it's a very, very strict process. Yeah? You have to do, for example, tests at TU Munich, which are not so easy to pass. You have to do in-track testing, operational testing, and all of these different tests. In the end, everything is checked really, really thoroughly. Like, again, a physician that is checking your health to the last bit. And recently, the approval was finally awarded. We're really happy about that. And now there's the only way is forward going into projects. Again, going back to the analogy of the Operation Slab Track, I think being here and looking at the railways, how far they have come from 200 years ago to now, they have really developed into the arteries, into the blood vessels of our modern society, and it's a really a huge economic value also that is often overlooked. A lot of people complain about subsidies for the railways, but essentially the railways actually enable modern life in many ways, and so it's important to keep these arteries open and to keep them running, to keep them in good health, and this is what we are here for. And so the only thing I can say is full steam ahead, and the Operation Slab Track is continuing. Thank you.
Thank you very much, Stefan. Thank you very much. Thank you very much, Stefan. Your presentations are always very amazing and engaging. And you have other seconds if you want to say something. No? Okay. Then I give the floor to the next speaker. Is Richard Stock from Plasser and Theurer, Plasser American, and the topic is rail management solution for slab track application and beyond. Thank you very much.
Thank you.
Welcome.
Thank you.
The floor is yours. Yes.
So good afternoon, ladies and gentlemen. After this really energetic presentation by Stefan, I will do my best to keep up the pace and keep you awake. And I will switch now your attention. We heard a lot about the track, slab track, life of the track. Let's now go one floor up to the rail and talk a little bit about the rail as being one of the core components. Why do we need to look also at the rail? We heard a lot about slab track life, 60 years, 90 years, 40 years, but we also need to look at certain components and how their life cycle might influence the whole life cycle of the track. And when we look at the rail, we have the rail wheel contact, and this will cause some problems. Plastic deformation, wear, cracks, thermal damage. All these effects will limit my life, limit the life of the rail. So we need to do something. We need to do rail management. And to be fair, from a rail point of view, and I'm a rail expert, it doesn't really matter whether there is slab track or ballasted track, because a lot of these problems will be the same no matter which track form you have. But of course, there will be some implications about slab track, and we'll talk about this a little bit later. So in our toolbox, we can look at the material, the joining technology, the profiles, the track quality, the friction management, the actual rail maintenance itself, and then all around this measurement technology and data handling. Let's get started. So the cornerstone of every new track construction when focusing on the rail is choosing the right rail grade for the right application. There are several rail grades according to the European specification available, a standard grade and several heat-treated grades that will have an optimized material structure for improved performance, which means higher resistance on the one hand against wear and plastic deformation, on the other hand also against crack formation. So by choosing the right rail grade from the beginning, you can do a lot of good. If you don't choose the right rail grade, you start with a lot of problems from the beginning. Okay, we need to join the rails, of course, because every connection in general represents a discontinuity. We can have classic rail joints. We've seen this in the presentation today. We have isolated rail joints, and of course we have welded rail connection as the preferred way of connecting rails. When talking about welding technologies, thermite welding, flash butt welding, in Asia also gas pressure welding as the main technologies. What's our goal? We want to create a long-lasting connection that has the same or at least the similar properties as the two rails that I connect. And for sure, I want to prevent premature damage, because I can choose the best rails. If the weld fails prematurely, I can't benefit from the properties of the rails. So the ideal joint, the ideal connection is something that the wheels really don't see, don't feel when passing over this. Speaking about welding, the process with the highest welding quality is flash butt welding. Profiles. With profiles, we can manage steering in curve, we can manage stability of vehicles in tangent track running at high speeds. I took the train today from Florence to Naples, great train experience. With optimizing rail and wheel profiles together, we can avoid conditions that cause high stresses, two-point contact, very narrow contact patches. And we can also deliberately move the contact from one area to the rail of the other, as we do with so-called anti-head check profiles, undercutting here a little bit the gauge corner, and again, delay rail degradation. When we look at different continents, we have different strategies. In Europe, we typically have 1 or 2 rail profiles per railway, or on the continent, however you want to see this. If we look into North America or Australia, we have a so-called multi-profile strategy dependent on tangent track, the high rail of the curve, the low rail of the curve, the sharpness of the curve. Track quality. We heard a lot today about precision, high precise track quality. This is a very important feature, and I think that's where Slab Track can contribute a lot by keeping this track quality over a very long time at a very high level. So how will track quality impact rail life? You can imagine if you have a really good track qualities, your trains run very smoothly, no dynamic forces out of this track, no dynamic forces acting on my rail and damaging my rail. Vice versa, if I have a really nice, smooth, well-maintained rail surface, the rail surface itself will not produce any unwanted dynamic effects that might damage my track. So having both of them at a significant level, they will benefit from each other. The system will benefit from each other. If I have one at a high level, but the other one is at a really low level, it will drag the other one down. So track quality, we could talk a full day about this, but not today. Friction management. We need to manage friction between wheel and rail. We need to adjust the friction at the right location to the correct level. So we want to avoid, on the one hand, high friction, because high friction would mean high contact stresses, quick damage development, high wear. We also want to avoid low friction condition in certain areas, because low friction could create traction issues. We cannot accelerate, we cannot brake safely. So when we look on the top of the rail, on the running surface, we want to avoid high friction levels, but keep the friction at an intermediate level to have safe acceleration and braking. So we speak of top of rail torque friction control with a friction modifier. If we look at the gauge phase, we want to reduce the friction to a minimum to avoid wear in curves where the wheel flanges are contacting the gauge faces. You can apply these products with onboard systems, with wayside systems. That's a North American wayside system here, to get this in the rail wheel contact. There is also something to mitigate low friction, especially in autumn seasons where there are a lot of leaves. We have the problem of these leaves getting pressed on the rail surface by passing trains, creating a really hard, black, slippery layer that really can create problems with braking, acceleration, with signaling. So there are also technologies at hand, like traction enhancers that are brought into the rail wheel contact, or simple rail cleaning with high pressure, water jet, laser systems, dry ice. There are several solutions out there to manage friction. And then finally, the rail reprofiling, the rail maintenance activities themselves. And these are the only measures in this toolbox we are just going through that can not just delay damage formation, but remove existing damage from the rail surface. Restore the profile, create a defined rail surface condition. We have different strategies we can pick from: preventive, corrective, regenerative, to get rid of defects like this. We'll look a little bit closer into technologies here now, because there are two main technologies: rail grinding, an abrasive dry process with rotating grinding stones, and rail milling, a non-abrasive dry cutting process with rotating cutter heads that are equipped with carbides along the circumference. And basically, these two processes achieve the same: a damage-free, well-maintained rail surface. Left grinding, right milling looks very similar, but the details differ. And again, it comes to specific capabilities and properties of each process, and this is what we'll look a little bit closer into now. So we always have on top rail grinding with the blue letters, and below rail milling with the blue background and white letters. So creating the transversal profile with rail grinding is very easy. You just align all these stones in a certain angular sequence and create this profile very flexibly with an accuracy of 0.3 or less accurate. With rail milling, the shape that I can achieve is provided by the negative shape of the cutter head plus the inserts. So this means for each individual profile, I need an individual cutter head. Creating an accuracy of 0.1 millimeter or less. Surface condition with grinding, we create scratches called grinding marks, and we create an according roughness, and we create these traces of individual stones, which we call facets. And with the process parameters, we can adjust surface roughness within certain parameters from relatively high roughness to low roughness. Milling itself, on the left-hand picture, creates a very characteristic groove structure on the rail surface, which is in general not a problem. When looking closer to this, a regular structure on the rail surface will always create some kind of noise effect, and that's not very favorable if you do rail milling and you have like a singing rail after each train when the train goes through. So rail milling machines have some kind of polishing process included, which can be usually some kind of grinding that just flattens out this rail surface. So with milling, we always create a low surface roughness due to this integrated process that creates this longitudinal polishing structure. A few operational parameter, about productivity, speed per pass, the metal removal per pass, and the number of required passes to achieve my desired metal removal. Grinding trains can move up to 32 kilometers per hour, and it's a bidirectional process, so we can grind in both directions. Average speed somewhere between 5 to 15 kilometers per hour. Metal removal per pass between 0.1 and 1 millimeter, dependent on the size of the machine. You can imagine a 6-stone machine can remove very little. A big production grinder with 120 stones can remove quite a bit in one pass. With milling, we are a little bit slower, a top speed of 3 kilometers per hour, and it's a directional process. This means one pass, setting back, doing my second pass. Average speeds between 0.4 to 2 kilometers per hour. However, with this process, I can remove way more if I want in one pass, up to 2 millimeters per milling tool. If I have a machine that has 2 or 3 milling tools per rail, I can remove accordingly more in one pass if required. What else is there? We have some byproducts. We have sparks with grinding, so I need to have some shielding. I need to have some firefighting equipment in the case of a fire. I need a dust collection system because grinding produces dust. Milling process itself is spark and dust free. The only thing that is created are these chips, but also these chips need to be collected with a vacuum system, stored on the machine, can be recycled afterwards. The polishing process, again, it depends a little bit what process you're using. It might have a little bit of sparks, it might not have any sparks or dust at all, but in the case it's a process that creates a little bit of sparks and dust, you need to have full housing and suction system as well. A few other aspects, every maintenance process creates process heat, and something will happen with this heat. In the case of grinding, this heat is absorbed by the rails, by the stones, and the sparks. On the rail surface, dependent on the process parameters, this can lead to very thin material transformations called wide edging layers. But grinding is not the only source of wide edging layers. Also, traction system of modern trains, when traction is according aggressive, can create these wide edging layers. This is still a very controversial topic of what damage can result out of wide edging layers or not, but one thing for sure, you will find these layers everywhere in track. With grinding, I can also treat a wide variety of track qualities and rail condition. With milling, the process heat is absorbed mainly by this massive grinding cutter head, milling cutter head, and the chips. Usually you don't create a wide edging layer. The polishing process might or might not create a little bit, but for milling, we need a certain level of track quality, or phrase it differently, we need a certain level of rail stability. Because in order to make a milling process successful, the workpiece rail must not be allowed to move underneath the cutter head. You can imagine if you have bad track quality and the rail starts to avoid this cutter head, the process will not work, or you might even damage your cutter head. So let's summarize this quickly. Grinding strengths. Full profile flexibility, bidirectional process, low to medium metal removal per pass, high productivity in scenarios where I only need to remove little to medium material due to the higher speed per pass. It's an established and integrated process. We can adjust the surface quality with the process parameters, and it's not really impacted by track or rail condition. On the limitation sides, yes, we create sparks, we create dust, so we need filter systems, we create sparks, so we need shielding and preventive measures. This might be of concerns in tunnels, for example. We put some heat into the rail, which needs to be controlled, and you can imagine in corrective scenarios where I need to remove a lot of metal, we need to do many passes back and forth, and productivity goes accordingly down. For the milling, the strength, we can choose low to really high metal removal per pass. It's a spark and dust-free process with an integrated by-product collection system. We have high productivity in corrective and regenerative scenarios that need a lot of metal removal. So this machine moves slower but can remove a lot of metal in one pass, creating a high surface quality, and it's a generally clean and low noise operation. What are the limitations? Reduced productivity whenever I need only to remove a little of material because it's a slower process. We have a low profile flexibility. In order to change from one profile to the other, we need to change the cutter head. It's a unidirectional process. For a second pass, I need to set back. The polishing might create some limited sparks, so I need their collection system. Cutting insert lifetime is usually lower than lifetime of a grinding stone on a grinding machine. And we have this certain track condition sensitivity. But nevertheless, it's just a question of using the right tool for the right applications of these two complementary technologies, grinding and milling. Okay, what else is out there? If you look at tramway tracks, we have the Atmo, which uses block stone technology, either in oscillating mode or in simple tracking mode. So it's just with some grinding blocks that are pressed on the rail surface, and then while this trailer is moving forward, they oscillate. What's the idea? Preventive maintenance between trains or once per night to keep the rail surface, only the top of the rail surface in a good condition, low metal removal. But again, this is just to keep a certain condition as long as possible steady on top of the rail. Reprofiling is not possible with this technology. Can also used to remove corrugation. Corrugation is like a wave structure forming on the rail surface. Then you need multiple passes. This specific trailer can be towed by any rail-bound or high rail. Please excuse me the word high rail. Live in Canada, so high rail means road rail vehicle. With up to 30 kilometers per hour. So we looked at all these tools that we can choose to apply to manage my rail life. However, very, very important, I need to know my rail condition. I need to be able to quantify my rail condition, because if I don't know what my condition is, I cannot choose the right technology to mitigate whatever is there. So measurement technology is key. Measurement technology for the transversal, for the longitudinal profile, for the surface crack condition, ultrasound to look into the rail, surface video for detecting some surface features and damages, then of course determining the exact location, data analysis and generation of measurement protocol. And what is connected with this is the capability to handle all this data. Because I might not just have one data source, I will have various data sources with various formats. I need to make sure I can check the integrity, link the data, process the data, synchronize my data then across all these different machines. And of course, in times like this, data and machine cybersecurity is one of the top concerns at the moment. Already mentioned data visualization, and then also transfer the data to machines for work execution. So we looked at these tools in our toolbox. Let's have a quick look now how these tools are used in an integrated process, from measurement to analysis and planning to execution, quality control, and then closing this loop and going through this loop again and again in maximizing my rail life. A small-scale process, small-scale integrated process is the so-called robot, which is an automatic local defect repair for rail and frock maintenance. It's a box-in-a-box system. It's placed on a standard flat wagon with a hybrid power supply. And this is basically including the whole process. You have somewhere a defect that was previously identified. The robot scans, does the analysis. There's an operator in there or two, then mills out the defect, preheats, deposit welds, grinds, quality control, and documentation. So small-scale integrated process in a box. Of course, side effect, it's a safe workplace, no one is out in track, and also counters demographic trends because you need less people working on such a problem. Let's look at this at the end on a more larger scale. So how is rail management done, was done, and is it still done? So we have some visual inspections, we have some measurement technology, hand tool or vehicle bound. We create some individual report. The railroads might already have some kind of strategy in place, cyclic or whatever, and there is a workforce experience, and all this data together triggers then the decision to maintain. The track is maintained with a grinding train. There might be an experienced or less experienced crew on there that does some on-site subjective adjustment. There might be some post measurements. And at the end of the day, we have created a shiny rail surface. and think everything is okay, but we don't really know. So when we do this as an integrated process, we start with the regular assessment of my rail condition, with rail-bound vehicle, with high rail/road rail vehicles, with trolleys that determine all these relevant data, condition data of my rail, which is then synchronized to a central place that does the data analysis, collects the data, helps you with decision-making, work preparation, provides you an overview as inspected. Again, then this data, out of this we have our work order, which is synchronized to the maintenance machine, but these maintenance machines also have measurement technology integrated so that they can live assess and live adapt their work orders to these conditions, because between here and here there might be some time, some change in the track condition. So the work is executed, QC measurements are done, it's again synchronized, a transparent documentation, a defined rail condition is created, and the report as maintained is done, and then the cycle starts again. So with this, we've reached the end of my presentation about rail management solutions for slab track and beyond. We looked at this toolbox for rail life extension. We saw that measurement technology is really very important. We looked closer into rail maintenance technologies to restore the rail condition, the grinding, milling, Atmo, the robot. We looked at data handling throughout the process, and finally drew a picture of an integrated rail management process for maximum rail life benefit. And with this, thank you for walking with me to the rail, a little bit away from the slab track, but nevertheless an important component. And with this, thank you very much.
Thank you very much, Richard. And this is a holy topic in rail. Now I call here on the floor Jens Kleeberg from RAILONE, Germany, Chief Sales Officer, with the topic Ballastless Track Solution for Renewal and Renewed Railway Tracks. Thank you very much.
If you want this, is it working? Yeah, it is. And this one is up and down. Okay. Well, welcome from my side as well. Thank you, Mr. Chairman, for giving me the chance to give this information today. Oh, there's the clock. Okay, I'm watching closely. Yeah, I'm always jealous about Plasser and Theurer because they don't have to say who they are. Everybody knows them, obviously. But for RAILONE, it might be different, especially in this environment. RAILONE is a company which provides railway tracks, especially ballastless tracks, but also concrete sleepers for ballasted tracks. We do that quite for a while. The company was founded in 1894, and then we at first supplied telecommunication poles as well as wooden sleepers, and from the 1950s onwards we changed it to, or started to produce concrete sleepers. In the early 1990s we started to develop our own ballastless track systems together with going international, so we left Germany, which is our home market, with sleepers but also with ballastless track technology, and 1999, where's this? We had this most known system, Radar 2000, which is a final development stage of earlier systems. 2004 we went into heavy haul traffic, and just a legal thing, in 2013 we were acquired by an Indian family company who is also producing concrete sleepers and doing track installation in India, which makes us today, I would say, a hybrid. Hybrid is the nowadays word, between a German engineering company and an Indian-driven business company, which is interesting combination, I have to say. Where are we? We are based in Germany, so we have production plants in Germany, 4 of them, but we are also active in Europe at several places, either on our own or with licensed partners, and we do have a plant in the US as well as in India. Obviously, we have partners in why is this sheet looking like this? Anyway, this is Africa, up here is Europe, Turkey, Saudi Arabia, India, and we are also active in Asia. So of course we are not in each and every country existent, but we are acting globally, and if you need us, we are probably closer than you would expect us. Okay, this about RAILONE shortly. ballastless track technology. What do we have? Basically, we do have two systems. One is a concrete-based system. It comes with the in situ cast, not precast, an in situ cast concrete slab. Many variations possible, so this is why I don't say it in general. Reinforcement, fiber reinforcement, dimensions for different track applications, induced cracking, whatever. So it's just an in situ cast concrete slab designed on the demands of the traffic mode that you find, and it comes with the bi-block sleeper, which can hold any kind of ray profile, which can accommodate different fastening systems, high elastic, low elastic, W shape, whatever. So again, independent, as said before, independent from the fastening system. So this is one system that we have, and we have another system which is asphalt-based. It has an asphalt load distributing layer, and it is on top of it you find a wide sleeper, which is quite a heavy block, similar to the IVES system that you've seen before, which is fixed horizontally. It's not merged into the asphalt. It would not be able to fix it anyway. So it's just fixed horizontally in longitude and in a lateral direction by a fixation block that I will show later on as well. So those are the two systems that we are dealing with, and as I said, they are available for any kind of traffic mode, especially radar, comes for tramways, for metro systems, for high-speed traffic, standard traffic, and since bit more than 15 years, 20 years now almost, for heavy haul traffic as well. We have installed it for roughly 3,000 kilometers worldwide in about 30 countries. And also homologated there, obviously, and as I said, it goes back to like 30 years ago, to the mid-90s. It does exist for switching, cross-six, for mass spring systems, so anything that you can think of, and we really have excessive knowledge and experience with this system. Just to give you an example, I don't know if this is true, but I think it's the only system which is used for any kind of high-speed train, being it a Talgo or an ICE, or the Shinkansen from the Japanese. What else do we have? So I think that's the only system which really is used for all these kind of high-speed trains. No, the Italian one is not. We don't have a high-speed reference in Italy. So okay, we have to work on that for sure. Just coming to my mind. The other system, GTRAC, by far not as experienced as the radar system, but still 250 kilometers for a ballastless track application, which is a niche product, still something. Main characteristic or main advantage of this system is that it's very rapid in installation due to the material asphalt, and it is mainly used on embankments and in tunnels and for renewal of existing lines. It does also exist for tramways, for instance, but mainly really for the renewal of standard traffic and standard lines. The main part of the presentation is today we're talking about ballastless track, and ballastless track, as I've shown, is there. You can discuss it. We had a patent discussion earlier, few years ago, and then we were confronted by a patent which was from the year 1900, exactly 1900. So when ballastless track has been established or invented, I really do not know. It seems to be old, maybe even from 67 Anno Domini. But what makes ballastless track successful, and I think in the last 30 years it really has established within the track system environment against ballasted track as well, but what does it make successful? And we heard a lot today about the design, and when I had black hair, when I started my career as a design engineer and a project engineer, I had a lot of discussion about the design, what a track system should look like, which components are working, in which way it is working, and so on. Nowadays, but then at that days in the 1990s, there was no ballastless track standard. There were barely any standard components. So that was really quite a job to convince someone about the design of a ballastless track system. Nowadays, having a standard, having experience over 30 years or maybe even more, having universities established and so on. I think the design part is something which is under control. I wouldn't underestimate it. But I think the design part can be done, and if you have an experienced engineer taking care of the known design rules, I think you can manage a ballastless track system. The other thing, components manufacturing, going into fastenings with the elastic clamps we heard today about Pandrol. I think these companies, and there are others obviously, like, you know, doing the W-shaped fastening system, they know what they are doing. There are suppliers of sub-ballast, elastic mats, elastic pads for the fastening system and so on. So if you take care of a proper choice of the material together with a quality assurance, quality control process of manufacturing these components, also for the slabs and the sleepers that we are doing, concrete is something which is under control. And if you have a proper quality management system, I think the components, core components of a ballastless track system are under control as well. One thing which makes it challenging, still challenging to my opinion, with respect to quality and to effectiveness, and it is of course a matter of the price in the end, is the installation process. And today I would like to give you some examples where we improved a lot compared to 30 years ago, but where we are right now, I think there's still, compared to the installation of ballasted track, there is still some space that we can improve. So let's have a look on the installation process as they were and as they are. So if I ask myself a question and I cannot answer it by myself because my intelligence is maybe limited, then I always ask artificial intelligence in the meantime. And I gave it a question: if I would have invented a construction machine as a synonym for a ballastless track system, and I can either use it myself as a contractor, as a construction company, or I give it to the market, what is the more effective way? What gives the higher benefit of this machine in the end? And but the details, I don't go into the details, more a game that I do. But what you see here as a result, the multi-criteria analysis, is if you say you have a technology, then give it into the market to people who can really make use of it, which would be a contractor, a construction company, then you probably have a higher benefit, at least for the product in the end, compared to if you just keep it for yourself and use it by yourself. And this is what we are basically doing since many, many years, to develop ballastless track systems, but also to make them available for the market, especially for the contractors. And AI seems to have confirmed this approach. So this is, again, what I said before. We are a system supplier who have really excessive knowledge on how to establish or how to design a system and how to make the homologation and choose the right components. But on the construction side, I think if you give it to a group of qualified contractors, construction companies, then they really can make the best use of the concept that we are providing. Anyway, let's have a look at the installation process and where we really made some benefits. As I said, we have the radar group with the in situ cast concrete slab and bi-block sleepers. It is installed top down. That means, as said before, the rail is held in position before you do the fixation of the track or the casting of the concrete slab. Before, of course, you have to lay out the track and bring it in in precise position, and then do the pouring of the concrete slab. Contrary to that, the system with asphalt, which we call G-Track, is bottom-up. So you at first build an asphalt layer, and on top of the asphalt layer, you lay the sleeper, you bring the rail, and you do the installation of the fixation block in the center. In detail, what are we doing? Left-hand side, initial installation of Radar 2000 in 1999 near Leipzig. These installation portals, heavy steel frames. I think each of them was 600 kilos. We thought that this is necessary to keep the track in position. Nowadays, I will show you, no, that was a complete misjudgment, but we were proven by contractors. And the other thing is, of course, the concreting with pump and so on. There are smarter ways in the meantime as well. For asphalt, it's a little different because asphalt was poured from the very beginning with standard road equipment, which is highly developed. So that is something which existed already in the 90s. And so that was used at that time as well. And for the laying of the track, since it is very similar, you receive a stable surface where you can lay the track. It was also done for one of the first applications with these movable portal cranes, which is standard ballasted track installation technology. So that D-track was from the very beginning done on a very mechanized basis. One thing that has changed or developed a little bit, and that is of course an essential one, because I think we all agree that the best welding is, sorry for Plasser and Theurer, but the best welding is the one that you don't have. So long rails obviously is the way to go for high performance track, high speed tracks. So you definitely have to deal with long rails, and what has been established in the past is either the construction with short rails or the construction directly with long rails, which means you have to bring them on site without having a track. If you do a new track, then obviously you don't have, it's new, so you don't have a track. And this means you have to transport the rails on site without rail equipment, which is something, but that has been found out in the meantime how to do it. If not, then you can work with short rails on islands, so from A to B with no rail connection and so on. So that is not an issue to install a track with long rails in the end in two ways. Of course, if you directly go for the long rails, then you don't have to do the second installation step of the long rails, which saves money, and of course you save the money for the construction rails themselves. So rails is something which is nowadays really a process which is, or long rails, which is under control for the installation of ballastless track on an isolated stretch. Another thing is just a short idea of removal of track. If you want to renew a track, this is a tunnel like 100 years old that you find in Italy, anywhere in the world, 100 years old, which has a tunnel invert, so you have to remove with standard technology the existing track. But that is a basis, that is a solid basis to install a ballastless track like E-Track if it is a tunnel invert, if it has some stability. And the other thing is always the drainage system. You have to see where it is, and if the tunnel is really, if you can manage the amount of water which is existent in the tunnel. But for the rest, clean the floor, and then you can install an asphalt layer directly on this layer. And depending on the accuracy of this tunnel floor, you either have to install 2 asphalt layers or only 1 at a height of 70 millimeters. This is an example of an existing asphalt track in the west of Germany, which was equipped with steel sleepers, and they were corroded, so they had to be replaced. And what they did is just took away the sleepers and then did a single grinding run, and then that was followed by, so this grinded layer was just completed by a new layer of, I think it was 60 millimeters or 70 millimeters of new asphalt in high precision, of course, and high precision means, you, again, as I said, you use the standard asphalt technology. However, you have 2 wires to both sides, although the slab itself is only 3 meters wide. Just to mention, our tracks have been installed in the meantime, as I said, in 30 countries, and I think it's more than 100 contractors who have installed our tracks. So some of them are mentioned on the pictures. Please, if I forgot any of you, it's not on purpose. It is just too much to mention here. Anyway, this is the asphalt installation, and what you do next is to place the sleepers, either logistical-wise, if you don't have a parallel track, which is existent here anyway, or like here, where you can take the sleepers from the train. You can also bring them with a truck, lay them down, and then put them over. And what you see here is the recesses for the fixation block in the center. Again, standard grinding technology, however, with a circular shape. And in this block, or in this recess, you have the blocks. We use concrete-based blocks. It's like a big ash tray. And they reach in this recess, and then in the end they are filled up with cement grout. And then basically you're almost finished, in contrary to that for radar tracks, which is a bottom-up system. You first have to install the track. An essential thing that you need to do is logistics, so how to bring in the materials. Most of the time on an embankment structure or something, you find enough space to have these staples next to the track. This is, of course, a perfect logistic conditions that you can ride on the track, so place the materials which you need, especially the sleepers, but you mostly find that in modern tunnels as well, because you have the evacuation path to the side. So this is how you do it, and then you just lay them on the ground. If you do not have the space to store the sleepers, then this frame, this panel installation has been done as well. This is, of course, a shorter panel with 18-meter length, something like that. But you can also make use of the faster and efficient track installation method. We frequently ask whether you can ride on a sleeper with an excavator, with the axle load of an excavator. That's a typical example of a cooperation between a contractor and a designer of a track. It depends how you treat the sleeper and how you support it. A monoblock sleeper, if you just support it in the middle, it will crack as well. And it's kind of similar with the biblock sleeper, but basically it can be done. And this is a typical example of a cooperation between us as a designer of the sleeper and the track and the installation company who is doing the construction work. So that can be done as well. For G-Track, as I said, installation with frames. And we had some talks, but I don't remember, with people from Plasser about having the G-Track track installed with these really powerful track installation machines. And of course, we have slightly different sleepers. They are wider, they are heavier. So we would have to modify let's say, the internal logistic or the transportation of the sleeper up here and to bring them down on the surface. But basically, that is possible if you would have an installation of a G-Track track in the respective scale. So that would be laying of track for radar and for G-Track. G-Track positioning, you lay down the sleeper, and that is before you do the installation of the concrete block. And the horizontal alignment is done by, there is barely anything more powerful, I'm almost finished. There's barely anything more powerful than a tamping machine. So running with the tamping machine, of course, without tamping, but using the precision or the placing tool of the machine is used to bring the track into the correct horizontal position. That's how we do it. And as Stefan has introduced before, we have a similar tool. A tamping machine would be too heavy for a Radar 2000, but it's kind of the same principle with the Versa and 2 points and a centric element in the middle. And then you can run with this one and place or position the track in a very high speed and a high precision that we need in the end. There's also an earlier version that you can see, which is from the year 2005, and this one is from nowadays. The installation itself, or the spindling, the track fixation, as I said, we had the portals before, way too heavy, so that is just done nowadays by simple spindles in different variants, maybe integrated in the sleeper or separate from it. What you can do with these spindles, you can also, and we saw that before, we can do an installation of the track in operation, which you see here. We barely do that for standard tracks because of signaling issues and. So normally a normal track, if it's installed, you close the line and then you do the installation and then you go, of course, as fast as possible. For drum base, we frequently have this, that we have permanent traffic and only block the track for, being it 6 hours, something like that, for the concreting work, but you can do that if you have somewhat more rigid sleepers and a pair of spindles to both sides, and then you can do the casting in between, and then you can permanently run on the tramway track if you do the installation like this. Concreting used to be like this. I know, 2 minutes, 1.5. Concreting used to be like this, still works. This is a recent picture from, I don't know, this summer. Of course, pump and so on, this is still frequently done. If you have a small stretch, just do it the standard way. However, of course, to increase the quality and also to make work easier and faster, because the concreting process is one of the slower processes, I would say. You can have these machines which are running on the rail, and then you do the concrete pouring in a very controlled way. And you see this one from the company of Rhomberg, where you have the concrete inside, the logistics in parallel. And I think I close with that one because the other one is just site information that you can have a look at by yourself. If you look at this one and imagine this one would be yellow, so a track laying machine, a track renewal machine, then basically we are almost there to be able to do a track installation on one track, whereas the other one remains in operation if we slightly modify, and we have seen some ideas today, we slightly modify the logistics and have it on the track itself. But if you imagine this installation train with the other element or with the other equipment beforehand, just self-propelled, running along the line, having the logistics from the other side. I can imagine that a renewal of a track from ballasted into ballastless track or from ballastless into a new ballastless track could be done on one line as well. So let's skip the other ones, not too much information anyway. Thank you.
Thank you very much, Jens. Okay, so we are a little late, but we have time, 5 minutes for the questions. I think that there were 3 very interesting presentation. I don't know if there's someone that has questions about this. Yes, one question, please. Maybe the speaker can come here, so it's can all see.
Hello, this is Jose Barrios from Bahntechnik in Switzerland. I have a question for both of you, actually, for Jens and Stefan. Let's start with Stefan. So you said you got the IBA Zulassung, the IBA homologation in Germany. Congratulations for that. And you also said you have sometimes pre-stressed elements for the IVE system and sometimes reinforced ones.
Yes.
So I guess in Germany you're using the pre-stressed?
Yeah, in the German approval we have the pre-stressing included in there. Yeah,
Okay.
because it's kind of tested like a sleeper, like a ballasted track sleeper. So the first crack comes too early in the 3-point bending test, and that's why it has to be reinforced.
Okay, that was
pre-stressed.
Exactly. So the restriction is not coming from the standard, like saying you have to have pre-stressed sleeper. It's more like you have to resist this moment when you do the test.
Yes.
So okay, so good. That's it.
But elsewhere where we don't have the same testing, like in Australia, we went for the non-pre-stressed version, and it holds. Because it was developed that way. That's why also it's not a sleeper-shaped piece. Yeah, it's quite hefty, quite thick for driving over it, but also for the resistance against the bending moments.
Okay, thank you. So second question actually could be also for you, but you can tell me, Jens. No, Stefan, it's okay, Jens. It's about this asphalt. I mean, you both have asphalt layer under the sleepers or under the elements. How long is the durability, the expected durability of this layer? Is it the same as in concrete? Is it longer, shorter?
Well, asphalt obviously has other material properties than concrete. It's plastic, it has other properties. We frequently find nowadays for ballastless track design rules that we have to demonstrate a durability of 100 years, which you on paper can do. There are the concrete standards are normally for 50 years, and you can extrapolate these rules so that it's durable for 100 years. And we were not asked to provide a durability of an asphalt track of 100 years, and thinking about the binder, I personally would have some doubts, honestly. But in general, you would think that this is possible. I mean, the experience that we have with asphalt, the first one was installed at what they called Nantenbach curve. It's south of Frankfurt, and that was installed in 1994. Perfect shape, it's perfectly in order. And later on Hannover-Berlin line, we have 2 years later, we have an installation as well. Again, perfect condition. So 30 years, definitely not an issue. 50 years as well. And of course, we have the experience from many roads. I mean, most of the ballastless track technologies are in concrete, whereas most of the road structures are in asphalt. So I really have a huge favor for looking more into asphalt as a material for ballastless tracks, because the material properties, because of the provenness, because of the installation technology which is existent from these many roads. So we really should take that into account and make more out of it. And 100 years, I personally do not know. I would have to check. In theory, I think someone can make an assessment for the binder. There's Mr. Freudenstein who knows more about it. But the other thing is, of course, a long answer on a short question, but the maintainability of an asphalted track is perfect. You remove the sleepers, you grind it, you make a new layer, and that can be done, I wouldn't say like the Salchev people in 8 hours maybe as well, but in a few days definitely you can easily renew a worn asphalt layer.
May I add something to this short answer? There is really good experience with asphalt layers also with the system Sato. That was already for 50 years in place and is working fine. Then on the now to be renewed Hanover-Berlin line, yeah, there's a lot of different systems, and the ones that are in really bad shape are the concrete-based ones, and the predecessors of G-Track like ATD, they are still in really good shape. Yeah? So this is another thing. And what a lot of people sometimes miss is when we know asphalt from roads, yeah? And railway engineers are not so familiar with asphalt. They are a little bit afraid. I have the feeling sometimes. Don't compare the loading in the street, on the road, with the loading under a G-Track, a sleeper, or an IVES block. Yeah? It's completely different ballpark when it comes to the pressures. Yeah? Because if you have a truck, you have 4 wheels, and each wheel has a contact area of 15 by 15 centimeters. Yeah? And this is how the whole load is transmitted. And it's always in a line. Yeah, that's why you get these indentations on a road. Sleepers and blocks that have a rail on top, they distribute the load a lot more evenly. And I think that's also very important to keep in mind when thinking about the durability.
Good, thank you. I have another question for Jens, actually. Talking about the renewal for Jens Kleeberg, yeah. Back to the concrete, as you said, you have a lot of experience. I mean, we all have in Europe a lot of experience. We have built a slab track for 60 years, more or less. And now there are many projects which are coming, like the one in Berlin with the REDA Renewal, the one we had in Switzerland with the Gotthard Passes Tunnel. So what are your recommendations for the REDA systems? Because I know, Paul, you showed it before, other systems as well. But for the REDA system, what's your standard procedure or your recommendations for the renewal of the tracks, which are coming anyways in the next 20 years?
We have one experience where we really had to remove the track because there was a fire incident with a restaurant wagon. What is it called in English? A wagon where you have a restaurant in and it catched fire. And it was standing on the Cologne-Frankfurt line, and of course they stopped the train, and then it completely burned down. So the track underneath, over a stretch of 50 meters, was completely demolished. You have temperatures of, I think, 600 degrees. Steel is deteriorated. So for this section, you really had to remove the track, and it's just immense power. That's the only thing that you have. You have the concrete, and even if it's damaged, cut it, make it smaller blocks, shift it, push it, hammer it. That's the only technology that I'm aware of. We're talking about construction technology, so maybe I'm looking more into the direction of the construction companies, but the experience that I have is really just use as much power as you have. But the thing is, if we look into repair concept, the nice thing about REDA is that in case the rail seat area, I mean, what can be damaged? Even if you have a heavy derailment, what can be damaged? The fastening system, if the fastening, if a guide plate or if it's a punroll base plate or something is damaged, you can replace it. It can be replaced. There's still the dowel in place and so on. We have many experience in the meantime with the rail exchange, so the dowel is still there, the fastening is still there. So anything which is related to a damage of a fastening system, no issue, just exchange it. If the rail seat area, these shoulders or the concrete shape is damaged, because we do have damages during installation. So there's construction trains, they are running on the track, and sometimes they derail, sometimes the two-way, these B-modular excavators are not properly railed, And so we frequently have damages on the shoulders of the rail seat area, and that can be reshaped, either with a steel profile or with concrete, depending on how much they are damaged. So I would say if you have a derailment, still no need to replace the track. Even if you cannot repair, and this is what we have done as well, and there are repair fastening system, even if, let's say, a longer stretch of the track is damaged or the rail seats is damaged, then between the rail, if a train is derailing, how is the track in the vicinity of the rail, under the rail, is it possible that it is damaged? So there's never a damage. So if you just grind, let's say you take away the rail, you grind it and do the repair fastenings between two sleepers, and then you have a direct fastening system, then you still have kind of a new or perfectly repaired track. So still no need to replace the track. That is done frequently if you have excessive settlements. Sometimes the substructure is failing and you have settlements, you stabilize it, but then you go between the sleepers and do the new fastenings, and that would be the repair method. So still no need to replace the track. Or the slab, the concrete itself, if you really have to go for the slab, which barely happens, I told you this one accident that happened, use power.
Thank you.
I have also a question for the both of you. My name is Paul Kamfraat. How do you provide the lateral resistance that's normally provided by the ballast on asphalt track?
Thank you for the question. So our blocks are quite heavy. They weigh 900 kilos per block. Yeah? So already by just sheer friction, there's quite a lot of force that can be transmitted. And the other thing is, I only mentioned it very briefly, there is a shear dowel that we introduce, which is like a steel pin, a steel tube, yeah, that is placed into a core drilling that you make in the asphalt. And it's 210 millimeters long, so it's as long as an A4 paper is wide. Yeah? And you stick that into the asphalt, and 9 centimeters stick out, and you place the block on top. I can show you like some details on my cell phone, but this is how we do it. And actually, the lateral resistance tests that we did, they show that we have a factor of safety of 5. Yeah? The requirement is 25, and we reach 125. So it's really stable. Yeah.
Thank you.
The lateral stability of an asphalt track, one thing, design process is always theoretic calculation, the other one is the practice. And of course we know that asphalt has plastic behavior, so if you permanently push it under certain, especially if it is getting warmer, then it tends to plastically move. So you have to limit these stresses to the least lowest or the reasonably lowest level. And the thing that you have seen with the G-Track system is a development which came over a period of 10 years, because initially we had a continuous longitudinal kicker, so this surface was even bigger, and then we made several tests with different sizes of blocks because we also wanted a longitudinal resistance, so we tested different sizes of blocks, and this one was the final result. Of course we did laboratory tests as well as in-field tests, and nowadays we have this experience of more than 30 years. In a curved track, you always do, when you do DB test sections, you mostly go for harsh conditions. So we have in a curved track, and this has proven by practice. Asphalt is something that proves by practice mostly, because material properties are not that clear as for concrete or steel especially. But by practice it has been proven that it remains stable, and this is what makes us confident that the lateral resistance is there. And of course you can increase the number of dowels. So if you go to a tight curve, normally we have it every second, it's straight every third sleeper, but you can go down to 1, and if absolutely required for whatever reason, then we would increase the size of the block.
Yeah, now one question which goes to Richard. How do you see the role of AI in predictive maintenance for slab track? A short answer, please, because we are running out of time. Sorry for the question.
So the short answer is yes, there will be a big role in this. How? We will find out. Honestly, we're still in the early steps of using AI for all kind of processes in rail maintenance, in track maintenance as well. So we could talk about this for hours, but yes, it will be a part. How much, we don't know yet. How useful it will be, we'll find out over the time.
Do you see any special points for at the moment where you say this is the most interesting point for me or for us?
We have several approaches, as I said, not just on rail maintenance, especially on there's TMC here, Track Machines Connected, that is working on this topic with rail testing. There would be several avenues we can go down. Will every avenue make sense? We'll find out, and we can't go down every avenue at once. So that would be the answer.
Okay, thank you.
Stay there. So Richard, I have a question for you. My chief is in Berlin, in Innotrans. He has to buy a machine, milling or grinding machine. Only one answer, not both.
The answer is, it depends. It depends on your requirements. No, there is no simple answer whether you need a milling or grinding machine. You really need to look at your requirements, what you want to do, and then decide whether you need a milling or grinding machine. There is no easy one solution fits all. That's not working.
Thank you very much. Are there other questions? I know that we are over time. Okay, then we stop here. The fourth session will be moderated from Marco Broglia. We do 10 minutes pause, break. Then we start again, I would say, 3 p.m. and 38. Thank you very much.